Okay. Hello, everyone. My name is Rico Landman. I'm a first-year PhD student at Leiden Observatory, and I'll talk to you about a project where we developed a self-learning adaptive optics control algorithm. So one of the main limitations of current and future extreme adaptive optics system is a temporal error induced by the changing atmosphere. This is caused by the finite time it takes to measure the wavefront, calculate the deformable mirror commands, and apply them on the mirror, while the atmosphere is changing in the meantime. This results in the so-called wind-driven halo, which we see in the figure on the right here, with a typical butterfly-shaped speckle halo in the direction of the wind. Another issue is our telescope vibrations, which cause tip-tilt jitter, which may lead to coronagraph leakage. Both of these issues can be solved by improving the control algorithm, specifically using predictive control. So we propose to use reinforcement learning for predictive control. So reinforcement learning uses a framework which is shown in the figure here. And I will formulate the AO control problem in this framework. So we have an agent, which is our deformable mirror controller, which operates in an environment. The environment is just all the dynamics around it, so the atmosphere, the servo lag, and everything. So at each time step, the agent receives an observation. This may be the wavefront sensor measurements or the reconstructed wavefront. Based on that observation, it decides on an action, the additional deformable mirror commands to put on the DM. Based on that action and the current state of the system, we observe a reward. We can choose whatever reward we want. For example, I can use the short exposure trail ratio in the focal plane as a reward. The goal of a reinforcement learning agent is to optimize the action such that we get the highest reward. That's the complete goal. So how do we do that? Well, in 5 minutes, I don't have time to explain the entire algorithm, but I will try to get the gist across. So we use an algorithm called deterministic policy gradient. So that's based on two models. We have the actor and the critic. So let me start with the actor. The actor is basically your controller. So it maps a wavefront sensor measurement or the reconstructed wavefront to deformable mirror commands. This can be any kind of differentiable parameterized model. So it can be just a linear model, or we include some domain knowledge in it. In my case, I use a recurrent neural network controller because that has some desirable properties for dealing with closed loop adaptive optics. This is modeled with some parameters theta. Secondly, we have the critic. Critic is basically your cost function, your loss function. So that models the expected return, so the strail ratio, for example, as a function of the commands we apply on the DM and the wavefront that we measure. So basically, this is just a forward model of your AO system. This can again be any kind of differentiable model. So what we want is to find the parameters theta that give for the observed wavefronts the highest strail ratio, the highest reward. So if we formulate it like this, and both of these are differentiable models, we can find the gradient of the expected future return with respect to the parameters of the controller. If we have the gradients, it's just an optimization problem. We can use a gradient-based optimizer to optimize the parameters theta to get the highest return. So we applied that. First, we applied it to suppression of tip-tilt vibration. So we have, on the left, we have the results from simulations. On the right, from experimental fabrication in the lab. So as the reward, we here use the deviation of the PSF center. So we want to minimize the tip-tilt jitter. So here it shows the residuals. We applied 3 vibrations along both the X and the Y direction and let the algorithm learn. So it shows the residuals along the X direction for 3 controllers. So on the top, we have for the trained reinforcement learning agent. In the middle, we have for an integrator with optimal gain. And on the bottom, we have the open loop residuals. So we see that the reinforcement learning agent is able to get rid of most of the vibrations, while the integrator is not. And we observe the same thing in the lab. So if we look at the temporal power spectral density, we see that indeed the reinforcement learning agent is able to reduce the power in these vibration peaks. So then we tested the algorithm for full wavefront control. So I simulated an AO system and I exaggerated the wind speed so that the dominant error term is due to the wind flow. Used a single layer atmosphere. As optimization objective, I used the short exposure, the Strill ratio on the focal plane. So on the figure on the left here, we see how the Strill ratio evolves over the training process compared to an integrator with optimal gain. We see that at the end of the training, the reinforcement learning agent can get a Strill ratio of factor 2 great. On the right, we here see the PSF for a 1 minute exposed simulation. And we can clearly see that for the integrator, we have that butterfly shaped pattern, the wind-driven halo, while for the reinforcement learning agent, it's almost gone. So to conclude, we show that reinforcement learning is a promising approach to data-driven predictive control, and that can suppress tip-tilt vibrations and reduce the wind-driven halo. Some key properties of the algorithm is that it's nonlinear, so that may be important for systems with a pyramid wavefront sensor to compensate for the optical gain. It's very flexible. We can choose whatever inputs we want to the model and the reward. So we can choose the reward of the Strill ratio, may even use the contrast, and can optimize for that. It's completely model free. So it does not depend on calibrations, misalignments between the DM and the wavefront sensor. And it's relatively efficient as it does not need very large matrix multiplications. But more research is needed on the performance under realistic conditions and how practical it actually is. Thank you for your attention. If you want to know more, you can ask questions or contact me.
Okay, thank you very much for this interesting talk. So we have a question by Scott Will. How long does it take for the reinforcement learning agent to converge? How much time is spent exploring parameter space versus exploiting?
Okay, so these are relatively old results. So here we see the training curve on the left. So for each iteration, we collect one sample and we do one training iteration. So you can see that after 40 iterations, it's already better than the integrator. So if we run at 1 kilohertz, it would be 40 seconds of data. And so I start off with I add Gaussian noise for the action to explore, and I slowly decay it over the training process. So it is learning while exploring.
Okay. For example, there's a question related to the regulator, so I will merge that with mine. So instead of using an integrator, you could have compared your method with something which is able to compensate for vibrations, because obviously the integrator is not able to do that. So this is the first question, and the second question is related to the reward function. I have a question from Carlos Correa. In a real system, where do you get the reward function from? In a reliable, noiseless way.
So the first question, indeed, we can compare it to something that we just choose a simple integrator with optimal gain as a simple baseline. We should compare it with other predictive controllers. On the second question, where do we get the result reliably? So yeah, that is indeed a consideration. We can also use the estimated residual wavefront variance from the wavefront sensor measurements. Could also be used as a reward, or use a short exposure Strill, which would be indeed noisy. So that it would indeed need more research on how realistic it is to use that.
Okay, well, so thank you. We may have other questions on the Slack, so I encourage you, of course, to look at that and answer these questions. So we have to move on to the next talks. Thank you very much again.